Hello everyone, I am Vivanchala. Welcome to my YouTube channel, Space Engine. This is a series of short videos in which I will explain some concepts about the universe. As such, theory of general relativity, dark matter, and particle physics. I will upload every day, so stay tuned. I hope you enjoy. Today's topic is star formation. The subject of star formation has undergone rapid development in the last few decades, spurred by instrumental advances that let us see deep into the regions where stars are forming. These regions are often obscured by dust and invisible to us in invisible light, requiring long infrared wavelengths or radio waves to penetrate. Our ideas of star formation historically were too simple. We imagined a nearly spherical and diffuse cloud of gas slowly rotating, collapsing along its pole, and forming a disk. Planets form the bulk of material, goes into a central star that switches on fusion. In practice, star formation is more complex because it occurs in large volumes of space where many stars form. Most of the stars we see are middle-aged, or in the heart of their lifetimes. The transient stages of star birth and death are difficult to observe and have only been observed with different techniques expanding the electromagnetic spectrum. As an example of star formation that we can see with our naked eye in our night sky in the winter in the northern hemisphere, but more easily in the southern hemisphere, consider the Orion Nebula. Viewed in optical light, we cannot see the star cluster, where high mass stars are ferociously forming from the condensing gas. Such a view is only possible at infrared or even longer wavelengths. The difference between the infrared and optical views of Orion and the Orion Nebula are dramatic. The reason for this is the very different properties of electromagnetic radiation of different wavelengths with respect to dust. Looking towards the center of a region of star formation with visible light is like looking through a closed door. Barely 1 in 1,000 or even 1 in a million photons can escape the dusty region, but infrared waves interact more weakly with the typical micron-sized dust particles in interstellar space. So infrared waves penetrate, and therefore we can see deep into these star-forming regions. There's a mechanism called induced star formation, where the event that triggers the collapse of a diffuse cloud in space containing gas and dust, but no stars, is the death of a nearby star. The shock wave emerging from the supernova event will compress the edge of a nearby gas cloud, and that can induce gravitational collapse. It's often said that the Sun is a typical star. Indeed, it is the closest star and gives us our most detailed view into how stars work. It's typical in the sense that it's converting hydrogen to helium, which is the job of many stars in the sky and in the Milky Way and in other galaxies. Other stars are converting heavier elements by the fusion process at higher temperatures in shorter stages of their life. Yet other stars, in collapse, are final stages of evolution, where there are states of matter quite unfamiliar to terrestrial regions. Every star that gains its energy by fusion for the time that it is doing the fusion process is in what's called hydrostatic equilibrium. This is the balance between pressure outwards from the energy released in nuclear reactions and gravity inwards at every point in the star. At every point in the star, that pressure balance is attained, so the star is stable. Stars are not bombs in any sense. We can only make fusion occur in the unstable transient mode of an atomic bomb. We haven't yet perfected stable nuclear actions that might give us fusion energy for our power needs. They are turning hydrogen into helium as a sun. Not only is the sun stable and not like a bomb, it's also regulated, like a thermostat. In terms of star properties, the fundamental attribute of a star is its mass. Mass determines everything about a star, from what type of fusion process occurs to its fate and eventual endpoint. Mass is actually the hardest thing to measure directly from a star, for an isolated star can only be done through a stellar model. But many stars are in binary systems, and the binary orbit and the parameters of the orbit give the mass of both components. In nature, the bounds on star mass are about 8% of the Sun's mass at the low end to roughly 100 times the Sun mass at the high end. Second fundamental property of a star is its luminosity, how many ergs per second or watts that it puts out in a particular wavelength regime or overall across the energy spectrum. This is called bolometric luminosity. The luminosity of stars on the main sequence, which is to say that stars are using fusion to convert hydrogen into helium, as the Sun has an enormous range going up to about a million times the luminosity of the Sun, down to about 1/10,000th of the luminosity of the Sun. Thanks for watching. Please share your thoughts and ideas in the comment section below. Bye.